All right, welcome back. We have made it. We have made it. You are now know everything you really needed to know about Math 131 for success, but we're going to have a final exam review just to get there. For those watching by video, we have our DVD. I've asked my group what they really want to concentrate on today, and everybody said optimization. But we're going to take it through the different things that we've done. This group is going to say if it's something we need to spend more time on, otherwise we will just sort of move on, okay? And everybody in here is going to prompt me about everything. Okay, the first thing, as you'll remember, that we did in the beginning was what kind of equations? Difference. Difference equations. And remember, we use difference equations when the same thing happened period after period. And that really made it, quote, like a compound interest, like compounded daily, compounded monthly, quarterly, or whatever. What we would start out doing is putting in words what was going on and draw our little time diagram so that we could get the hang of what was going on period after period. Remember, if you started out an account, we did mostly money. If you started out an account with some money, that was your Y sub 0. We called Y sub n the balance after n periods, where everything was happening the same every time. We would go to the first period, and I would encourage you to say, is that years, quarters, months, or whatever, so that you stay on top of what your periods are. And when you started a difference equation, you would look at what you start with, what happens from the beginning of the period to the end of the period. If you made a deposit or a payment into an account, you noticed it. You came up with your new balance. Y sub 1 would be the balance at the beginning of the first period. Actually, yeah, at the end of the first period and beginning of the next. Then you'd see what would happen. Go one more period. So you get the hang of what was going on, but we needed a difference equation. So we would come down here at Y sub n, describe what happens to get to Y sub n plus 1, and that's how we wrote our difference equation. Normally, we'd say Y sub n plus 1 equals whatever you have at the beginning of that period, plus, and for all the problems we did, most of them were money, so we would say interest on Y sub n, and then plus any deposit or minus any payment that was made at the end. All right, and if this was a population, what normally happened instead of interest, it would tell you how the country was growing or how it was disintegrating, really. You know, people were dying out, whatever happened in here, or people coming in, same number of a year. All right, so our difference equation, we then simplified to A Y sub n plus B. And that was how you could iterate one period. You could find Y sub 0, Y sub 1, Y sub 2, Y sub 3, one period at a time. Remember all that? Iterate the terms. All right, but then if you needed something like Y sub 40, and you didn't want to iterate one term at a time, we went from the difference equation to the solution. And that's where we solve for Y sub n, like Y sub 45, the balance after the 45th period. All right. Impress me. What's the formula for Y sub n?
E over 1 minus A plus Y sub 0 minus B over 1 minus A times A to the nth power.
A to the nth power, yes. A to the nth. And usually you were either solving for like the balance after the 25th period. Sometimes you knew that you were getting like a home loan, and you were making payments of size B, and you might want to know how much could you borrow. That would be when you'd solve for Y sub 0. Or maybe you were going to go out and buy a car and you knew the price of the car and you needed to solve for B and you would know at the end of the loan, what would that y sub n be? If you got a loan, what's the ending balance after your last payment? 0. You would make your y sub, if it was a car loan for 36 months, y sub 36 would be 0, and you'd be able to solve for y sub 0. If you knew y sub 36 was 0, you could solve for how much you could borrow. All right, everybody remember this and okay. We also learned to graph based on the difference equation and given y sub 0. And you looked at A. Well, first thing you did was you looked at that little dotted line, which we would say the curves would approach, be attracted to, or repel. Remember that? But if A is bigger than 0, which is this little part right here in the solution, but if you were just looking at this part, if A is bigger than 0, what does that tell you about your curves? Are they going to oscillate or be monotonic? It's going to be monotonic. If A is positive, you're raising a number like to the first power, second power, third power, a positive number. So your graph is going to be monotonic, meaning always increase. Or it could always decrease if this value right here were negative. Okay? All right, but for graphing, you just looked at this. If A is negative, so you're raising a number like -2 to the first, -2 squared, -2 cubed, and so you know then it's going to oscillate. All right, so the first thing you did for the graphing part, A greater than 0, you knew automatically it was either going to always increase, ... or always decrease, ... going down. Okay, then you looked at the absolute value of A being bigger than 1, or the absolute value of A being less than 1. Now, absolute value of A being less than 1 meant between -1 and 1, so you would be taking a number like a half. And if you raise a half to the first, a half squared, a half cubed, what's going to happen to this term right here? It's going to get smaller and smaller and smaller, so the value of the function is going to start to approach b over 1 minus a. So when the absolute value of a was less than 1, this thing starts to get real little, and the points start to approach or be attracted to b over 1 minus a. When the absolute value of a is bigger than 1, such as 3 or 4, this number you're raising to a bigger power, so it's going to be b over 1 minus a plus this thing, which is getting bigger and bigger and bigger, so it would be repelling that line. Remember that? Okay, now, I just had a question from WebAssign. Ooh, look, the ink went right through the page, so I'll flip over. This is from the section on difference equations. This is a WebAssign question, and it was from difference equations. And the question was number 6 in those exercises. All right, and I can put it in front of you, and I'm in control of the in and out today, so if we're in a different classroom if you're watching this by DVD today. All right, and I'm in control of the ins and outs. Here we go. If you can see it, Carolyn has just retired and has, is that $1 million? $1 million in her retirement account. The account will earn interest at an annual rate of 6% compounded monthly. At the end of each month, Carolyn will withdraw a fixed amount to cover her, next page, expenses. And the question was not the first question, but the second question. All right. So what is the maximum amount that Carolyn can withdraw each month if she wants her savings to last indefinitely? Indefinitely. We don't want her account to go down to 0, but we always want the money to be there where she can remove the same amount every month. What are you guys thinking? Yes, you're going to make 100 on this test.
I hope so.
That is good. All right, so your thought was, when I'm thinking of the graph, this line is y oh, y'all have to help me out here. Okay. Y equals b over 1 minus a, and we call this the constant graph, the constant. If your dots are always right here, this is constant. Constant. Okay, So if you're on a constant graph, that means that you put in some money, it's going to earn interest, but what you're going to do is take away the interest, and y sub 1 will be back to exactly equaling y sub 0. All right, so you can actually work this a couple different ways. I personally think if you're thinking about that your money is going to last forever for your children to fight over when you leave it to them, when you die, you realize that all that's coming out is the interest. So in this case, this is exactly equal to the interest you're going to earn on that money. All right, so how did we figure out the interest in here? I equals PRT. I equals PRT. Okay? So, she is just retired. She has $1 million. So this amount right here is $1 million. The account is going to earn an interest rate of 0.06, 6%, compounded monthly. So this N is 1 month. So in our equation, I equals PRT, T represents time in terms of years, so T will be equal to 1/12. All right, so our formula will be that will be the easiest one, 1 million. The rate is 0.06, and the time is 1/12. So on the calculator, I have 1 million times 0.06. Whoops, I just hit a light off. There we go. All right, times 0.06 divided by 12. And we have $5,000. Okay, so the question really is, the second part of this question was, what is the maximum amount that she can withdraw each month if she wants her savings to last indefinitely? And the answer is $5,000. Does that make sense for you? You could have set up the difference equation and found your A and your B and put it in your B over 1 minus A, and that would have done it for you, or just knowing what she would pull out every time would have to be equal to the interest. Is that good enough for you?
Yeah.
Okay, so the key here was indefinitely. Otherwise, you had to use your difference equation. All right, can somebody in here ask me another question about difference equations, or are we good to go? Good to go. All righty. Well, this ink is good. It goes right through the page. All right, so for the next things, I was going to take the textbook and go to the, if you look right here, I've already tabbed a few places. I went through every section in the textbook, and I'm going to let you tell me if you think we need to go there. All right, and don't forget you ask questions also. All right, first place I went was Chapter 0. Chapter 0, and I'm on page 43. And let's see if I can zoom in on this. On page 43 in the textbook. And I think I picked this out because it had all those good old negative exponents that you guys have worked with all semester. This is Chapter 0. And this, these are just properties of exponents. Would you mind scanning this in your book and tell me if there's a problem on this page you think you need to review with your exponents? Page 43 is one that need to practice, because you remember all through the semester we work with exponents. Anything on page 43? Anyone? Which one?
37.
Number 37. Okay. It's 8/27 raised to the 2/3 power. Y'all saw that several times during the session, didn't you? 8/27 to the 2/3. Okay. All right, so I'm on page 43, problem number 37. And we have 8/27 raised to the 2/3 power. And what you're remembering is the property A raised to the m over n is equal to the, what root? Nth root of A raised to the m. So here, 8/27 means you're going to take what root of 8/27? The cube root. And then what are you going to do to it? Square it. All right, so the cube root of a fraction, as you remember, is the cube root of the numerator over the cube root of the denominator. So the cube root of 8 is 2. The cube root of 27 is 3. 2/3 squared is 4/9. Okay, it's remembering that property, converting from exponential form to radical form so that we can figure out what's going on there. Okay? All right, anything else on that page anybody needs to see? Okay, I also have the back page 44 marked for some reason. I think I was carrying over to the top of 44 is what I was looking at. Anything here?
Number 69.
Which one?
69.
69. Well, let's try this blue paper and see if that works better. Okay, we're on page 44. Problem number 69. We have negative 27x to the 5th raised to the 2/3 all over the cube root of x. All right, this is taking into account a lot of properties of exponents. First of all, when you had a times b raised to the nth power, you have a to the n, b to the n. So we have a product here raised to the negative 2/3. And then it looks like we're going to have a division problem. So remember a over b. It looks like we're going to have some exponents go in there. So looks like we'll have some bases the same. So a to the m over a to the n is what? A to the m minus n. Okay. Remember this negative in front of the 27, you could think of that as negative 1 times 27 times x to the 5th. You might prefer to think that. It's up to you. So we'll have negative 1 to the 2/3, 27 to the 2/3, x to the 5th to the 2/3, all over x to the 1/3. Okay, I'm using power of a product in the numerator. All right. If you want to convert it to your roots, you'd have the cube root of negative 1 squared times the cube root of 27 squared. And I think the next one's easier, just using power of a power. A to the m raised to the n is a to the mn. So I'll just leave that as x to the 5th to the 2/3. All right, here we go. Cube root of negative 1, everybody? Negative 1, and then you square it and you get positive 1. Cube root of 27? 3. 3 squared is 9. And then x to the 5th raised to the 2/3 is x to the 10/3. And we have that over x to the 1/3. All right, so now we have 9. And this is all multiplication. So we have x to the 10/3 divided by x to the 1/3. That's our property for division. So x to the 10/3 over x to the 1/3 is x to the 9/3.
Oh,
Right.
yes.
Let's write out x to the 10/3 minus 1/3 using our property for division. So that's 9. X to the 9/3. 10/3 minus 1/3, which is 9x third. Okay? All right. All right, let's move on off the exponents in chapter 0, and let's go to section .06. Section .06. All right, this was we're on page 52. Page 52 in the book. And this is the section that you really used later for optimization. And you had your figures, and it was helping you remember the formulas for the figures. And I have circled a couple that I thought you might want to set up, and you can choose to do that or not. First one I picked, and let me see if you're interested, is number 11. Okay, consider the rectangular box in exercise 3. That would be the one right here beside it on the page. This particular rectangular box has a square base. Okay. In number 11, it says, consider that square base rectangular box with no top. Write the expression for the volume of this square base box with no top. So take a second and do that. Then I'll catch up with you. Hey, so that we all are using the same letters, let me just make up some letters here. All right. If it's square base, let's just call the bottom a x by x, and we'll call this a h for height. Okay? All right, so what is the volume of this box? X squared h. You get the area of the bottom and multiply it times the height. Right? The volume of anything that we have that goes straight up, get the area of the bottom, multiply it times the height. Okay? All right. No, the rest of number 11, it says, write an equation expressing the fact that the surface area of this box with no top, surface area is 65 square inches. Okay, write your equation for the surface area of this square base box with no top. All right, what parts go into this box that we're looking at the area of? The bottom, the two sides, and the faces, two faces, front and back faces. Okay. All right, surface area means what's the area of each of these parts. So what's the area of the bottom? X squared. Now the side is right here. So what's the area of that side? Okay, one side is XH, but you got two sides, so it's 2 times XH. And then what about the front face here? Okay, and we got a front and a back, so 2XH. And it told us the surface area is going to be 65. So 65 equals X squared plus 4XH. Okay, and you'll remember when we got into the optimization problems, we might be restricted on the surface area, but we were trying to maximize the volume. So then you would find some way to get this into the formula for volume. All right, and we'll probably do some of those once we get to that section. All right, the next, is that good, everybody? The next one I circled on page 53. Page 53, number 17. And it says, consider this corral. Here's goes to this figure. Okay. It says, suppose the fencing for the boundaries of this costs $10 per foot. So this would be the boundary. And the fencing for the inner part, inner portion partitions cost $8 per foot. Find the expression for the total cost of the fencing. All right, so let's just make up some letters so we're all together. We'll call the boundary part here a X. So around the outside here is X. And then the parts inside here we'll call Y. Okay? All right, so the question is to define the formula for the total cost if the boundary parts around the outside are $10 per 1 foot and the fencing on the inside parts are $8 per 1 foot. Everybody got it? Excuse me? Oh, my work's not on the screen. Okay. Let me pass that up. All right. So if this is X feet right here, how much does it cost for this side? It's X feet, and it's $10 per 1 foot, so the cost of this side is 10X. And we have another one of those right here, don't we? So we'll multiply that times 2. 2 times 10X. That's those two parts. And then what about this top part and the bottom part? That's still on the boundary. So what would that be? Okay, this is a Y and this is a Y, and it's 10 times those two Y's. So we'll have 2 times 10Y. So that's the boundary part. Okay, now on the inside here, that's $8 per foot, and you have, what, 2 Y's here? So we have 2 times the Y, and that's going to be $8 per foot. Everybody good? Mm-hmm. And that would be how we come up with the cost function for that particular one. Everybody good on that one? Okay, let's go to problem number 25, and if you guys see something else you'd rather do, let me know. I just picked a few of these. This has to do with cost, revenue, and profit. The average sale at a small florist shop is $21, the average sale. Okay, so that just means every time somebody comes in, they spend like $21 on the X items. Okay, X is the number of sales per sale. So the weekly revenue is 21 times X, X the number of sales in 1 week. Okay, so the weekly revenue, 21X. The corresponding weekly cost is this function in dollars. How do you figure out what the profit function is, everybody? Profit is revenue minus cost. And I know you can do this because I've harped on it so much, but let's just make sure that you tell me what's wrong when I set this up. Okay, let me move this up, zoom out a little bit. What's wrong with my equation? Profit equals, you just told me that that is revenue minus cost. Revenue is 21X, cost is 9X plus 800. Somebody tell me what's wrong with that.
9X plus 800 has to be in parentheses.
Thank you. It's revenue minus the whole cost. If you mess up on your parentheses, it's going to hurt. So you have 21X minus 9X minus 800. Be careful to set things up in parentheses. Okay? All right, that's all I think we need to say about that one, unless you think there's something else. All right, I flipped over to the end of the exercises, chapter 0, and just wanted to point out problem number 17. This is page 56. 56. Okay, chapter 0 is a good place to go review your algebra, as I've said all summer session. Find the points of intersections of these two curves. How did we use that later?
Regions bounded by curves.
Finding the areas of regions bounded by curves. All right. And just remind me how you find the points of intersection of these two curves. Set them equal to each other. What does the graph of y equals 5x squared minus 3x minus 2 look like? parabola, is it open up or down? Up, and you know the y-intercept is -2. And now you know how to quickly find the vertex by using your derivative and setting it equal to 0. Back in chapter 0, you used a little formula, x equals -b/2a for the x-coordinate of the vertex. Didn't you memorize that? All right, what's the graph of y equals 2x minus 1? Line, y-intercept's -1, slope is 2, up 2/1. Okay, all right, so you know how to find the points of intersection. Everybody good on that? Okay, the next thing that I have marked is from chapter 1. Chapter 1. Okay, this was the section that in derivatives, page 134. And this is where we were talking about a derivative as a rate of change. And the one I've just circled is problem number 21. We're on page 134. And it said, let f of t be the temperature of a cup of coffee t minutes after it has been poured. Interpret f of 4 equals 120. F of 4 equals 120. All right, somebody tell me what that interpretation of that is.
When it's been 4 minutes, it's 120 degrees?
Yes, after 4 minutes, the temperature is 120 degrees. And then it says the derivative at 4 is -5. So we were supposed to estimate the temperature of it's T in minutes, T in minutes. All right, I didn't want to do this part. Let's estimate the temperature of the coffee after 5 minutes. Since T is in minutes, let's do after 5. If f of 4 is 120, the derivative at 4 is -5, what would be the temperature supposedly after 5 minutes? Had you used that derivative there? Remember when we sketched a graph, T is in minutes. This is temperature. And we started out with the point 4, 120. At 4 minutes, the temperature was 120. The derivative at 4 is -5. Remember, the derivative means change in what? Temperature over change in minutes. So if the derivative is -5, that would be degrees. Change in degrees. Degrees per, am I off? Degrees per minute. All right, thanks. So if the derivative at 4 is -5 and you kept up with your, what the slope means, change in temperature, which is in degrees, over change in minutes, it's saying at the time of 4 minutes, the coffee is dropping 5 degrees per minute. And I feel like if you draw your little coordinate system, it helps. So based on that, you could say, well, the temperature after 5 minutes is approximately equal to what? You're at 120 degrees. Over the next minute, you expect it to drop 5 degrees, so it should be down to approximately 115 degrees. Remember that tangent line approximation that we did? I think half the key was thinking of the derivative as change in whatever the y is in terms of over the change in whatever the x is in terms of, and then you could get it there. All right.
What page is this?
We're on page 134. Page 134. And that happened to be problem number 21. All right, the other thing that we did was we could write the equation of the tangent line through there. Remember the equation of the tangent line? And then you could estimate anything. You could say y minus the y coordinate, which we called it temperature, so big temperature, equals the slope, -5, x minus the x coordinate, and that's time, so I'll do little t for time, minus 4. So then you could estimate the big temperature anytime using that tangent line that came through the curve, minus 5t, I'll put parentheses, minus 5 times t minus 4 plus 120. Then you'd have a good approximation for the temperature. All right, that was using your derivative as a rate of change so that you knew how you could approximate values real close. Everybody good? All right. Let's see, the next little thing that I did was I went to the end of the chapter review, and I'm on page 138, end of chapter review, and this was just finding the derivatives. Do you see any problem? I've marked number 39, but do you see anything up here that you feel like you need to do for finding derivatives? Okay, I've marked number 39. You name it if you see something else you'd rather do up there. 31. Okay, number 31. All right, write it down and go for it, and then I'll catch up with you. Number 31. All right, what rule are you starting out with, everybody? General power rule, because we have something raised to the 10th. So you brought the 10 down, rewrote exactly, decreased by 1. Did you stop there? No, you got to do the derivative of the inside. So it's times the derivative of the inside. The derivative x to the 5th is, 5x to the 4th. I was about to miss that one. Minus, and now how are you going to find the derivative of x minus 1 to the 5th?
Bring the 5.
Okay, general power rule again. So bring the 5 down, rewrite, decrease by 1, and the derivative of x minus 1 is 1. And there we have it. Okay, so you had a general power rule inside a general power rule. Everybody good? Okay, probably number 39 we don't need to work all the way. Any questions on that? Probably don't need to work 39 all the way out. I just need you to tell me what to do. Okay, so f of t is 3t cubed minus 2t squared, and you're finding the derivative at 2. What do you do, everybody? Find the derivative first, and then put your 2 in, because you got to find the general formula for the derivative, because it says find the derivative and then evaluate it too. All right, number 56. I just want to know what these instructions are asking you to do. Find the second derivative. Your variable is p. And what is the second derivative going to be anyway? You can look at that one and tell. First derivative is 3. The second derivative is 0, so there's no evaluating p at 4 anyway, but I just wanted to make sure you were okay with that. All right, let's go to page 139, number 77. All right, when you evaluate limits, you had 3 little outcomes in this class. Remember, you do your plug and chug? Plug and chug? That's not in any books, but that's what you do. All right, when you plug it in, if you just get an answer like 2 or 10 or 0 or 17 or whatever, are you done? Yes, that's the value. That says the value of the function is the same as the limit, okay? But what happens like in number 77 when you plug and chug, you're going to get 0 over 0. What happens when you get 0 over 0? Indeterminate form, and what are you going to have to do?
Simplify.
Find a way to simplify. And your examples were factor, and this one factors, or it would be a complex fraction that you had to simplify, or sometimes you had to rationalize a numerator, get the radical down in the numerator. Those were the three cases you saw in this book. Okay, what about, let's see what happens in number 3. It's 78. If I put a 3 in there, isn't that going to give me a 1 over 0? I think it is. 9 minus 12 plus 3. Yeah. All right, number 78, when you plug and chug, you get 1 over 0. What does that tell you? It does not exist. It's going to either head to positive infinity or negative infinity, but if it goes different ways, you just have to say does not exist, 1 over 0. All right, so 0 over 0 is indeterminate form. 1 over 0, it does not exist. Okay, this one definitely wouldn't, because by the time you factor it and look at it on each side, it's going opposite directions, so your only answer there would be does not exist. Okay? This end of the chapter review did not do anything with going to infinity, so I wrote out some myself. How about as x goes to infinity of x squared? This says the limit as x gets bigger and bigger. This, remember, the x squared is what the y value is. Y is x squared. So what happens to this y value as x gets bigger and bigger? Where does this thing go? Infinity. Okay, let's look at the other one I wrote out here. As x goes to infinity of 1 over e to the x. All right, let's go to the denominator. What does e to the x look like? Just the graph of y equals e to the x. Right, it's the exponential growth. So as x gets bigger, e to the x gets really, really big, right? So 1 over a huge number goes where? Towards 0. So as x goes to infinity, 1 over e to the x goes to 0. All right, the next example. The limit as x goes to 0 from the right of natural log x. Let's get a visual on the graph of y equals natural log x. Find a piece of paper here. A lot of times if you can see the picture, it's easy to do. Oops, let's go out here. All right, remind me what the graph of y equals natural log x looks like. Remember, it's your inverse of your natural exponential function. Where's your asymptote? Yep, graph looks like this. Goes through the point 1, 0. So here's the graph of y equals natural log x. So what is the limit as x approaches 0 from the right of natural log x? So a little bit bigger than 0 is right here. So as you get closer and closer to 0, from this side, the y value is headed to negative infinity. Negative infinity. Very good. Okay, so you got a visual of the graph on that. All right. Any questions from Chapter 1 that you had? Anybody? Chapter 1. All right, the next little group that I marked off. This will be your fun set here. I've marked off the optimization problems in Chapter 2. All right, I'm in the supplementary exercises. This is what everybody's excited about. Page 213. Page 213, and the first one I would suggest that we look at is, I've marked a lot of these. Problem number 55. We're just going to do some setups. Page 55. An open rectangular box is to be 4 feet long and have a volume of 200 cubic feet. Find the dimensions for which the amount of material needed to construct the box is as small as possible. So what am I minimizing? It told you, surface area. And this other information here is giving me some information about my open rectangular box. All right, go for it and I'll catch up with you. All right, we have an open rectangular box. It is 4 feet long. It is to have a volume of 200 cubic feet, 200 cubic feet. All right, so that's going to be the restriction on our box. It's got to be 4 feet long, or you might have called the other 4. It really doesn't matter. And the volume is 200. All right, so let's get our formula that goes with this 200. That's not what we're not maximizing or minimizing volume because we're already given it. All right, you want to call this an X and an H? All right, so what's going to be the formula for my volume here? 4xh equals 200. All right, this is my constraint equation. All right, constraint equation. All right, now what we want to do is minimize the amount of materials. So we need to work on the surface area. And remember, this is what we need to minimize. So we need to get a formula all in terms of one variable and then take the derivative, set it equal to 0, etc. All right, surface area. All right, this box is open. So what's the surface area of the bottom? 4x. Okay, what's the surface area of the two sides? Okay, 2xh. And what's the surface area of the front face and back face? Okay, we got 2 of the 4 h's. Is that correct, everybody? All right, so that's not going to clean up much better. All right, this is what we need to be able to take the derivative of and set equal to 0, but there are too many variables, plus that represents every box there is that is 4 feet across the front. We need one that holds 200 cubic feet. All right, which variable you want to solve for? H. Okay. H is equal to 200 divided by 4x. And I think if we go ahead and reduce that, that'd be easier. What's that, 50 over x? H is 50 over x. All right, so surface area then is 4x plus 2x, and in the place of h, we put 50 over x plus 8, and in the place of h, we put 50 over x. So surface area cleaned up looks like it's 4x plus, what's that, 100 plus 5 times 8 is 400 over x. And remember, let's go ahead and bring that x to the -1 up to the x up to the numerator, so when you take the derivative, it's going to be easier to do that. All right, should we go another step or two, or can we stop there? This is the main thing that all of you tell me you have trouble with, is getting the equation. Then you know how to take the derivative and set it equal to 0. Everybody good?
So when minimizing, you take the derivative and set
If you're going to, whatever you're going to maximize or minimize, you're going to take the derivative and set it equal to 0, because on your curve, that's where you're going to have potential max and min points, and that's why you set it equal to 0. Okay? Are you good?
I think so.
All right, let's set up another one. I was going to do 57, but that's volume, so let's move on to inventory control. Let's try number 59. Remember, you're going to have you got a geometric figure, you got an inventory control, you got a cost, profit, revenue kind of deal, or yield, and we'll look at one of those. And what else? The demand equation. All right, number 59, inventory. Publishing company sells 400,000 copies of a certain book, and they're telling you how it ties up storage and space and all this stuff. Okay, so then getting down here. Setting up each production run cost $1,000. The carrying costs figured on the average number of books in storage are 50 cents per book. Find the economic lot size. That is the number of production runs that minimize the total setting up and carrying costs. So you got to come up with what it costs to set up and cost to carry, and we want to minimize that. Okay, go for it, and I'll catch up with you. Have you forgotten how to do that one? Some of you are smiling. Or does that mean you're happy?
No.
Not feeling so happy. There is a lot to review. All right, everybody got your book open so I can remove mine? Okay. All right. So we're going to have to figure out the production size. We're going to do inventory control. And it tells you right in the last line, we're going to need to minimize the total setting up cost plus the carrying cost. Okay, so we got to come up with inventory control, which is setting up costs and carrying costs, and we're going to need to minimize it. So we need to get this formula, and then we'll take the derivative. All right, if we stay just like we did when we were going over these, we said X is number of books, in this case. X is number of books. R is the number of production runs. Okay, so we've got books, copies of certain books. So X times R in our problem is equal to what? Number of books times the number of runs, and that has to add up to how much in a year? 400,000. So altogether we're going to have 400,000 X times R. Now, what is the average number of books in storage? If we order X books at a time, what's the average number? X over 2. All right, so let's do the setting up cost. Running off the cost in several partial runs throughout the year result in added costs for setting up. Okay, setting up each production run costs $1,000. So what's your inventory cost going to be for running at R times per year? What's the setup cost? It's $1,000 per production run, and how many production runs are you having? R. So it's going to be 1,000 R. Okay, plus carrying cost. It's going to be 50 cents per one book. And how many books are you going to have in storage at a time? X over 2. So we'll have to go 0.5 times X over 2. All right, so that's going to be my cost for inventory. What's the problem here? Too many variables, plus we are restricted to a total of 400,000 books throughout the year. So shall we just solve this for R? R is equal to 400,000 over X. So we get 1,000 times 400,000 over X plus 0.5 times X over 2. All right, that's the formula for inventory cost based on the number of books per run. So if you just chose to do 10 books at a time, this is what it would cost you per year. Or if you chose to do 100 books at a time, this is what it would cost you per year. But you want to be very efficient. You want to find out how to minimize this. So what do you do, everybody? Right, find the derivative. Set equal to 0, solve for X. Okay, and that would tell you number of books. You can put it back in here and it will tell you number of runs. Now it says find the economic lot size. That is the number of runs that minimize the carrying cost. So you want to know number of books and number of runs. All right. Everybody good? Answer is yes. Okay, let's go to problem number 61. That's at the top of page 213. So we're getting in an example of each type. Okay, top of 213, problem number 61. Profit. Suppose that the demand equation is P equals 150 minus 0.02x, and the cost function is, find the value of x that maximizes profit. So you're going to maximize profit. Okay, so get your profit formula. All right. The instructions are to maximize profit. So immediately as soon as you hear profit, the general formula is revenue minus cost. All right. The only thing we have is the demand equation, which is an amount of money from the sale of the items. So what is revenue with respect to that price per item? P times X. And I'll go back and put what that is in just a second. Okay, revenue minus, and cost is 10x plus 300. Everybody remember your parentheses? Hope so. P is 150 minus 0.02x times x. That's revenue minus the cost. Be very, very careful with all your parentheses there. Okay? All right, that's the formula for profit. And, of course, where you take the derivative, I would distribute and clean up. Don't forget that's 150x minus 0.02x squared minus 10x minus 300. And that would be 140x minus 0.02x squared minus 300. All right, so there's your profit function. You remember you're going to take the derivative with respect to x, set equal to 0, and you got it made. All right, mistakes always seem to occur because people forget that revenue is the price times x, number of items. They forget the x, and then the other part of the mistake is using the parentheses to distribute the negative. The concept's pretty easy, it's just that a lot of people forget the x. Okay, everybody good? All right, let's look at number 63, and that's the fourth type we worked with. 63. Travel agency offers boat tours to several Caribbean islands. Since the temperature around here last week was 105, did y'all know that? On Friday it hit 105 degrees. This would be great. All right, for a group of 12 people, the cost is, for each additional person above a 12-person minimum, the cost per person is reduced by $20 for each person in the group. The maximum size is 25. Okay, so they won't go out on the boat if you don't have 12 people, and they don't have room to sleep but 25. So what tour group size produces the greatest revenue for the travel agency? Set up your equation. This one has a restricted domain on it. All right, this is number 63. We're on page 213. All right, first of all, it told us that we can only have between 12 and 25 people. All right. Now that means that when we solve this for the number of people to maximize our revenue, if our answer comes outside 12 and 25, then we have to be sure to check out the values at 12 and 25, because a absolute max might occur where the derivative is equal to 0 or undefined, or at an endpoint. You remember for a graph, let me just do one real quick. If you were graphing a function with a restricted domain, it might look like this. Well, if you have a restricted domain, here's a relative max, here's a relative max, and this one turns out to be the absolute max. You have a relative min here, but you have an absolute min at the endpoint of a domain. So where you set the first derivative equals 0, it only would give you these values. But if you are restricted, then it might occur at an endpoint. So in this problem, once you find out what x is from our work, you need to check out the profit at 12, or revenue at 12, and you also need to check out the revenue at 25, as well as the revenue at the x value you find, or the number of people, to see which one is really going to bring in the most. All right? Okay, so let's set up our problem. I don't think I wanted to use x, because we just used x as our unit of increase and decrease for these problems. All right, so for revenue so far, revenue. Currently, if you have 12 people, they got $800 per person. Okay, cost. So the revenue, if they did it at 12, let's just go ahead. I've marked all over this with my marker. All right. Who knows? 12 times 800. So the revenue at 12 is $9,600. All right. Now that's if you do nothing. Let's let x be the increment, that's an increment of increase, decrease. All right, it says for each additional person, so 12 plus x will be our number of people. For each additional person, the cost is reduced by $20 for each person in the group. So what will the cost be? 800 minus 20x. So 800 minus 20x will be the cost. Okay? So that is our revenue function. Now we could go ahead and figure out the revenue at 25, right? 25. That means x is 13 here. When x is 13, that would send us to 25 people. Is that correct? If x equals 13, number of people is going to be 12 plus 13, or 25. So let's see what the revenue at 13 is, which is going to come out to be our revenue at 25 people. All right, so we would have 25 times, all right, 20 times 13, 260. So it's 800 minus 260 is 540. And 540 times 25 is 13,500. All right, so if we had 25 people on there, we would have $13,500 in revenue. All right, I just figured it up with 25 because this is the formula for revenue where x represents the unit of increase. So if x is 13, there's your 25 people. And so if you got 25 people, the revenue coming in will be, the cost will then be $540 a person, and the revenue coming in is $13,500. All right, but there's your revenue function, and we want to see, these are the endpoints of our restricted domain for revenue. You want to know if there's something in between here where you have a derivative equal to 0. So just as a quick review, what kind of rule might you use to do the derivative here? Product rule, because it's 12 plus x times 800 minus 20x. Let's get the derivative. First, what's the derivative of the second? Negative 20 plus the second function times the derivative of the first. All right, you just clean that up, set it equal to 0, come up with x. Once you know what the x is that sets it equal to 0, put it in this value right here. X plus that tells you number of people, and check out the revenue. Whichever one of these gives you the maximum revenue will solve the problem. Everybody good? All right, those are the 4 types of optimization problems. 4 types. All right, I'm watching the time, so we need to truck on, don't we? All right, I'm at page 242. This is Chapter 3, Integration Techniques. And I'm just going to, let's just talk through how you work some of these. All right. I think you know what to do here for finding the derivative. It's going to involve a product rule with a general power rule. Everybody good? Product rule with general power rule. Number 11, we sort of just did one like that. Would you do your general power rule first? And then inside you got what rule? Quotient rule. What's the quotient rule? Okay, some of you are yodeling, some of you are not. Bottom times the root of the top minus top times the root of the bottom, and over the bottom squared. Okay, so chapter 3 was, we just did 2 sections there, right? Product and quotient rule. All right, let's see, did I have something on the back? No, I didn't really. That was, all right, chapter 4. I'm on page 274. 274. This was your natural, exponential, and log functions. You guys were pretty good at that. On number 13, I was just trying to, it says simplify. What is e to the 8x times e to the 3x? When you distribute here, e to the 8x times e to the 3x. E to the 11x, base of the same, add the exponents, and then 7 plus 7 e to the minus 2x times e to the 3x would be 7, what? E to the x. All right, number 23. I don't think we did one like this. Differentiate e raised to the e to the x. Take a second. Differentiate. You're using your good little chain rule, right? All right, what's the derivative of e raised to some function? E to that function times the derivative of that function, which is e to the x. Everybody got it right? The derivative of e to the u is e to the u times the derivative of that u part. How would you go about doing number 57, the log of an awful expression, x times e to the x divided by square root of 1 minus x? What would be a good thing to do before you start differentiating this?
Can't just do natural log of x e to the x minus natural log square root 1 plus x.
All right, so you're going to apply your properties of logarithms to write it in simplest terms. So you have the natural log of the numerator minus the natural log of the denominator. And then when you had the natural log of x e to the x, then how did you go further with that? Natural log of x times e to the x. Natural log of x plus natural log of e to the x. What is the natural log of e to the x equal to? X. And then, remember, you used all those properties, simplified, and then took the derivative. Very good. How'd you handle exponent on that 1 plus x, the log of 1 plus x to the 1/2 that was down in the denominator?
You can move it to the front.
Move that 1/2 to the front. Don't forget that once you've used your properties of logs, you have not taken the derivative yet. You just found a simpler way. Did anybody on the test, I forgot to look, anybody just use all your properties and then forget to take the derivative? I think you guys are good. All right, any questions from chapter 4 that you had in mind? All right, I think it picks up the pace here because you've done this more recently. Okay, I'm on page 314 in chapter 5. 314 in chapter 5. I think everybody thought this was easy. All right, 314, chapter 5. The atmospheric pressure at height x miles above sea level satisfies the differential equation, not difference, but differential. Find the formula, which I told you was the solution to the differential equation if the atmospheric pressure at sea level is 29.92. So what would your formula be, everybody, for P at x? What's P at x? What's your formula?
P naught.
P naught, which is 29.92, e to the negative 0.2 x in this case, e to the negative 0.2 x, because x is your variable. Solution to the differential equation. Anybody recall any concerns from chapter 5? All right, the next thing I have marked is, our integration on page 366. Integration on 366. What do you get when you integrate 3x, integrate 3 squared dx? The derivative of 3x squared is 0. Yes, 3 square x. That's just a constant, right? 3 squared is 9. You integrated 9 dx, you get 9x plus c. Okay, how are you going to integrate number 11?
X raised to the 1/2.
Okay, it's 4 minus x raised to the 1/2, and what kind of integration do you need to go with?
U to the
U, yes. U, which is 4 minus x to the 1/2 dx. All right, somebody had a question for me on substitution. Before I get there, let's look at number 32. This was probably easy for you. How do you set up the definite integral to find this area? Whoops, they didn't tell you that point of intersection there, did they? I'll go ahead and tell you it's 1. I can look at it and tell it intersects there at x equal 1. All right, so you integrate from 0 to 1, what?
X.
Square root of x minus x squared dx plus dx plus you integrate from 1 to 1.21 x squared minus the square root of x dx for finding the area between the two curves. All right? Okay, here's a problem that was given to me before class for integration. I want to be sure we get there. This came out of, I don't know if it was WebAssign or homework. 3x squared times x cubed plus 1 to the 1/2 dx. Sorry, I'm going to do this because it goes right through to my book. Let me move the book out of the way so you're not distracted. I'm coming. Throw away this. All right. The integral of 3x squared square roots of x cubed plus 1 dx. And the question was about integrating this. Okay, it's either going to be a u to the r, e to the u, e to the u. Which one is this one going to be? U to the r. All right, so remember we want to convert everything to u's. What do you think the u is? X to the third plus 1. So remember, as you do this, come right underneath and make your substitutions. Okay? All right, then before you do anything else, you always go over here and find the derivative. The derivative is 3x squared dx. At this point, what do? Thank you. Y'all are so good to remember this. You look both ways. And you see a x squared and a dx, and a 3x squared, and there's the 3x squared dx, so it's exactly equal to du. So we are going to integrate u to the 1/2 du. We've switched it to something easy, so when I add 1 to 1/2, I get u to the 3/2. Divide by 3/2 is the same thing as 2/3. All right, so we converted it from looking hard to something easy. We got an answer, so now we're ready to say what this integral really is, which is 2/3. U is x cubed plus 1. We'll raise that to the 3/2 plus c. All right, you had told me after you got to this part, you got confused here, but I think you're forgetting to look, because if you forget, you're going to be sad. All right, is that good? That's a lot easier when I do it, doesn't it? That's my job, make it look easy. All right, let's still back on page 367. Riemann sums. All right, this was a midpoint. Know how to substitute those values in? Everybody good with Riemann sums? Midpoint, left point, right point, putting in the numbers. This is your function. Any questions? Everybody good? All right. Next little place I marked was, this is a review of what we did last class period. Whoops. I'm not good at this, am I? All right. Suppose that money is deposited steadily into a savings account at the rate of $4,500 per year. Okay, so it means all throughout the year, you put in a little bit all along so that it sums up to $4,500 per year. Determine the balance at the end of 1 year if the account earns 9% interest compounded continuously. Somebody remind me how you're going to do that. You're putting in it a little bit at a time so that during the course of the entire year it comes out to be $4,500. It's not $4,500 at the beginning or at the end, but a little bit all along. It's compounded continuously. What are you going to do?
Integration.
You're going to sum up from 0 to 1. Basically what's happening is you put a little bit in all throughout, and this is just going to go for 1 year. But that amounts to, by the time you make your last little deposit, $4,500. Okay, so it'd be $4,500, what?
E
to the 0.09 t dt. All right. It's not going to be probably a whole lot more over $4,500 because you're just putting in a few dollars every day to add to your account. So in the beginning, you're not getting much interest there. Everybody good? Compounded steadily. Compounded continuously at a steady rate. All right, the next little place I marked, was some more U substitution. Oh, no, number 55. I just got the signal. We're about out of time, so let's go to problem number 55. Find the present value of a continuous stream of income over the next 4 years. Gosh, they were too nice to you. They told you everything here. Where the rate of income is 50 e to the negative 0.08 t, $1,000 per year. What are they telling you? And the interest rate is 12%. Oh, you know what? They told you that, okay, they made this really interesting in that people aren't putting the same amount in every year. They start out with that negative right there. This is like how many dollars, $1,000 per year goes in. So they start out putting like maybe $50,000 a year, the next year they're going to put in less, and the next year less. That's why they gave you an amount here. But let's just change it and say that you're going to put in a total of $100,000 per year. Those were the kind of examples we looked at. All right, so that's how much is actually going in, and the interest rate is 12. So you're looking for present value. What's your formula going to be, everybody?
Summation of.
Okay, you're going to sum up over the next 4 years, so 0 to 4. You're putting in a total of 100,000, the units are thousands of dollars per year, because I changed the problem. E to the rate is 12%, but we're going to the present, so it's going to be negative 12t, negative 0.12, 12%, negative. All right, negative r, negative 0.12 t dt. Does that make sense, everybody?
Why is the 12
Because we're going to the present value. We're looking at a PV as opposed to a FV. FV is positive, e to the positive 0.12 t. If you're going to a present value, you're discounting. You're moving to the left. All right, everybody good? Everybody happy? Ready for your exam? Maybe not this moment, but you will be. All right. You guys have been a pleasure. I really appreciate you participating in these sessions, and so do the people watching it by DVD. And I look forward to good grades on the exam, and have a happy life. That's very important.